Okay, Richard. So
Mhm.
if you are ready, I will introduce you.
Oh yeah, sure. I'm ready.
Okay, very good. So welcome everybody. Okay, Richard gave a beautiful series of lectures last week about Ricci flow, and today we have the pleasure to hear his lecture on compactness and partial regularity theory of Ricci flows in higher dimensions. So
Yeah, thank you, Gerard, for the invitation and the introduction. So in this talk, I want to present a new compactness and partial regularity theory of Ricci flows in higher dimensions. So let me just give you an outline of the talk. So first, I'll want to provide some motivation for the problems that I'm going to consider and some history, and then I'll state the main results, and then so then these results may not be may contain a lot of new terminology, which I will only try to give you. Will only be able to give you the intuition for in part 2, and then in part 3 I'll try to give you a bit better definitions of what these new pieces of terminology are, and try to introduce a new perspective on the geometry of Ricci flows that becomes important when we look at these new kinds of theorems. And I'll also provide a few more details on the main results. The talk will cover 3 papers that I've posted on the archive last summer or fall, so you can see a list of them down here. All right, so let me start with part 1. First of all, I'm going to be interested in solutions to the Ricci flow. And one important question when we study Ricci flow is to understand the singularity formation if somehow the flow ceases to exist at finite time and develops a singularity. So that's one big question that we want to understand. So for example, in dimension 3, that led to the resolution of the Poincarean generalization conjecture by Perelman. And another question that's also important is the study of the long-time asymptotics if the flow exists for all times. Right? So these are the questions that I want to, that I care about, some of the big questions. And so this has been done in lower dimensions, and in general, this is often done via what is called a blow-up analysis. So a blow-up analysis, let me just review what this is. So this is a technique that's used very often in particular in geometric equations. I would describe it as follows. So here I try to sketch a Ricci flow. So the x-axis should denote m, and the y-axis should denote time. And it's assumed that we have a singularity at time t that's indicated by this dashed line. Then what we can do is we can find a sequence of points xi, ti in space-time that's, as I would say, run into the singularity. And by this, I just mean that the curvature along these points blows up. Okay, and so now in order to study what happens near these points, what we could do is we could, choose a sequence of rescaling factors, lambda I, and then parabolically rescale the original Ricci flow by lambda I, okay, and time shift it so that this point corresponds to a time 0 base point. And then we could hope that maybe in some sense or after passing to a subsequence, these rescaled flows converge to a limiting flow. And this limiting flow then has to exist for all non-positive time. So it has to be ancient. And this flow is often called a blow-up model or a singularity model. Okay? And so if we are able to, if we somehow can classify these flows or have some information on these flows, then this will give us information on the geometry near these points. Okay? Okay, so the upshot here is that the blow-up analysis allows us to reduce the study of the singularity formation to the study of to some other classification or study of singularity models. Okay? And so this is something that I'll be using throughout this talk. I should also say that in contrast to many other geometric equations, until recently, performing a blow-up analysis was actually quite tricky in Ricci flow. So we were not able to choose these points xi and ti and factors lambda I as we wished. So we had to be extremely careful because there's somehow this corresponding compactness theory only worked if we had local curvature bounds. So there was an extra step, which is often called point picking, involved, and so that we had some difficulties in performing this. So and this will you'll see later that that the new theory will do away with this issue. Okay, so but maybe I'm getting ahead of myself. Let me just discuss what do we know about singularity models in lower dimensions, or so what do we know in general? Well, in dimension 2, singularity models can be classified. So they're just the round shrinking sphere. And so correspondingly, the only way that we can have a singularity in dimension 2 is by approaching a round shrinking sphere. Okay? And so this was done by Chow and Hamilton. And then in dimension 3, maybe the singularity analysis is somehow the most famous one. And in dimension 3, it was shown that blow-up models are kappa solutions by Perelman, and that those were subsequently characterized, and then this led to the the construction of Ricci flow with surgery and the resolution of the Poincarean geometrization conjecture. So so there's the whole story here. Okay? So what do we know in higher dimensions, or in any dimension? Well, we don't know much, but we know that one very important candidate for blow-up singularity models are what are called gradient shrinking solitons. So, and a gradient shrinking soliton is, if you haven't seen this before, it's just a Riemannian manifold equipped with a potential function such that this equation holds. So we have an extra Hessian term, but otherwise it looks like an Einstein metric with positive Einstein constant. Okay, so for example, the round sphere would be an example here, rescaled appropriately. And in this case, we would just choose f to be constant. But we could also have metrics that are not Einstein as gradient shrinking solitons. And so the reason why we care about gradient shrinking solitons is because we can find a sequence, a family of diffeomorphisms from M to itself. More specifically, they're generated by the flow, the flow of the rescaled gradient vector field, such that if we pull back this metric G by these diffeomorphisms and then rescale by the metric, and we're looking at all of this for negative times, then this family of metrics satisfies the Ricci flow equation. Okay? So this is a self-similar Ricci flow, so all time slices are homothetic, and the Ricci flow develops a singularity at time 0. Okay? So it exists for all negative times and develops a singularity at time 0. Okay? So the basic example here would be, again, where we have the round shrinking sphere. So f is constant in this case. So gradient f is 0. And then phi of t would just be constant in t. And then we would just see the round shrinking sphere that develops a singularity at time 0. Okay? Right, so what do we know about this corresponding self-similar Ricci flow? So first of all, more or less, we have a curvature bound of the curvature blows up like constant over the remaining time. So this is often called a type 1 singularity. And then we could also ask, well, what are the corresponding singularity models of this self-similar Ricci flow? Well, if we parabolically rescale this Ricci flow, we just get the same Ricci flow back. And then if we take a limit, we just again get the same Ricci flow back. So in other words, the singularity model of this flow is just the flow itself. Okay? And so that's why these flows are so interesting, because their singularity model is their own flow. Okay? Okay? And so this shows us that if we want to understand singularity models and of Ricci flows, then we have to understand gradient shrinking solitons, because every gradient shrinking soliton occurs as a singularity model of at least its own flow. All right. And then in addition, let me just give you one maybe slightly more complicated example of a gradient shrinking soliton. So this would be a round shrinking cylinder. So in this case, I take a sphere of dimension bigger or equal to 2, cross a Euclidean factor. Yeah. And then I just equip this with the corresponding Cartesian metric, product metric, where the SK factor is rescaled appropriately. And the potential function f is just going to be a quadratic function on the Euclidean factor, which compensates for the lack of Ricci curvature. But we could also just look at the gradient of f, and this would just generate dilations on the Euclidean factor. And if we now look at the corresponding Ricci flow starting from this metric, then we would get a Ricci flow where just the sk factor rescales, but the rk factor, Rn minus k factor remains constant. Okay? So, but modular rescaling or dilation on this Euclidean factor generated by the gradient of f, this is just the multiple of the metric. Okay, so in other words, this metric, despite not being an Einstein metric, somehow shrinks modulo rescalings, reparameterizations on the Euclidean factor. Okay, and so the reason why somehow we have been able to understand Ricci flows in dimension 2 and 3 so well is in part because gradient shrinking solitons in these dimensions are all of this form. So they're either spheres or cylinders. Okay, but in higher dimensions, they may be more complicated. All right, so this is called a type 1 Ricci flow because somehow the curvature blows up at the scale c over t. So what we could do is we could say, well, we could study so-called type 1 general Ricci flows and ask what their singularity models look like. Okay? So a type 1 Ricci flow is just a Ricci flow that has a singularity at time t and where the curvature satisfies this bound. Okay? And then it was shown by several people that in this case, when we take, it's possible, it's much easier to take blow-up models. Okay? And all these, when we take the blow-up models appropriately, then all singularity models must be gradient shrinking solitons. Okay, so in this case, we somehow have the reverse, that not only every gradient shrinking soliton is a blow-up model, but that in some sense, in some sense, if we take blow-up models correctly, then these are gradient shrinking solitons. Unfortunately, this bound is relatively unnatural. It is not implied by any other geometric condition. A slightly more natural bound would be if we just impose an upper bound on the scalar curvature of the same form. And this is implied, this is, for example, the case for in the Fano case, in the Keller-Ricci flow Fano case. And in this case, it was shown that all singularity models are again gradient shrinking solitons, but they may have a codimension 4 singular set. Okay. So this leads us to the following conjecture, that maybe we can completely remove these curvature bounds and get that somehow for a general Ricci flow, in some sense, most singularity models, and I need to make this more precise, of course, are gradient shrinking solitons. Okay. And so the goal of this talk will be to verify this conjecture in a certain sense, and I hope you'll agree with me that this is going to be an optimal sense. All right. So, okay, before attacking this conjecture now, let me show you a few examples of singularity formations in higher dimensions, so just that we can adjust our expectations. Right? And so the first example that I find quite interesting is an example constructed by a former graduate student of mine, Alexander Appleton, who showed that there exist Ricci flows in dimension 4, whose blow-up limits he could completely classify. And so these Ricci flows are U2 invariant, so they only depend on 2 functions, one-dimensional functions. So he was able to characterize them relatively well. Okay, so what are the possible blow-up limits? Well, they are the Iguchi-Hansen metric, which is a Ricci flat asymptotically locally Euclidean metric, or R4 modulo Z2, so that's an orbifold, or with an Euclidean orbifold, with an orbifold at the origin. So if we mod out by Z2, I just mean a mod out by the reflection about the origin. Okay? So that's also the cone over RP3, or it's the asymptotic cone of the Iguchi-Hansen metric. Then further blow-up models could be the Bryan soliton modulo Z2. So that's the Bryan soliton again, modulo the reflection about the origin. So that again has an orbifold singularity at the origin, or RP3 cross R, so essentially a cylinder. Okay, so just to recap, these 2 blow-up models are Ricci flat. These 2 blow-up models are singular because they have this isolated orbifold singularity. And these ones are the only gradient shrinking solitons. Okay, so if this Vogler conjecture was true, then these 2 guys would be somehow the answer. Yeah? Okay? So you may be a bit surprised that this guy here is in the list. This is a gradient shrinking soliton because it seems like it's flat, so the Ricci flow should just be constant. But somehow the idea here is that Well, every single time slice is invariant under rescaling because it's a cone. So we could also view this as something that shrinks under the flow, modulo dilations. Okay. All right. So you may have noticed that I've put these two guys into parentheses, and that's because in Appleton's work he could show that these four models could show up, but he could only show that these two models have to show up. So there were basically two different types of behavior. We're not able to say which behavior occurs. And then depending on the case, we either see these four models or only these two models. Okay? And nevertheless, it's somehow conceivable that there are cases where only these two models show up. Okay? So then the only answer to this folklore conjecture would be this degenerate singular gradient shrinking soliton. Okay, so we may have to have some singular set in these gradient shrinking solitons. So this is what I wanted to take away. And then somehow this idea was later reinforced by, basically at the same time reinforced by Stolarski, who constructed Ricci flows in dimension 13 or higher, whose only gradient shrinking soliton blow-up limits are Ricci flat cones. Okay? So again, if the folklore conjecture remains true, we need a singular set in the limit. And then there were also results by Li, Tian, and Zhu, who constructed Kähler Ricci flows that have to develop a singularity, but for complex geometric reasons cannot converge to a smooth gradient shrinking soliton. So again, here's the conclusion. We need to allow a singular set in the folklore conjecture, and we need to allow for these degenerate Ricci flat cones. Okay, so let me now go ahead and just revise the folklore conjecture. Still a little vague on this most word, but at least now we're saying that any Ricci flow, for any Ricci flow, most singularity models are possibly singular gradient shrinking solitons, where the singular set has codimension at least 4. Okay? So Appleton's example would somehow be the optimal case where the singular set is a point in a 4-dimensional type slice. Okay, so I'm going to prove this result, or I'm going to show you in what sense this result is true. And it turns out, in order to prove this result, somehow the most important tool, or what's at the heart of this conjecture, is a new compactness partial regularity theory for Ricci flows. Right? So essentially, what I'm going to need to do is I'm going to introduce this theory to you, and then somehow it's not hard to prove the folklore conjecture once we have that theory. So I'm going to spend most of my time on this compactness partial regularity theory. And so before doing this, I will also move a step backwards, and I'm going to show you a compactness and partial regularity theory for a different type of objects, namely for Einstein metrics. And I'll do this for two reasons. First of all, just to recall what compactness and partial regularity theories are about. Okay? And so many of you may have seen the case for Einstein metrics already. And then secondly, well, every Einstein metric somehow easily gives rise to a Ricci flow. So if we want to understand these properties for Ricci flows, then we have to understand compactness and partial regularity properties for Einstein metrics. All right, so with that being said, let me now recall the compactness and partial regularity theory for Einstein metrics. And so the following results are due to Gromov, Chigar, Kolding, Neighbor, and Tian in several permutations. All right, so what does it say? Well, let's consider a sequence of pointed complete Einstein manifolds. Okay, so I'm going to normalize the Einstein constant. Then we know that these manifolds have uniform lower Ricci curvature bound. So we know that we can pass to a subsequence and obtain Gromov-Hausdorff convergence to a limiting pointed metric space. Let me call this X. Okay? So X could a priori be very irregular. Right? It's just some metric space. However, if we impose an additional assumption on the sequence of Einstein manifolds, namely if we impose a non-collapsing condition, which I'll express by a uniform lower volume bound for points for balls of a uniform radius around the origin, then it turns out the space is much nicer. And it turns out that in particular, the space can be decomposed into a regular subset R and a singular subset S, such that the following is true. So first of all, R is actually given by an open smooth manifold, and there's a smooth Einstein metric, I'll call it G infinity on R, such that if we restrict the metric space metric D to R, then we get the length metric of the Riemannian metric D G infinity. So that's a very strong result actually. So this is due to Chigger and Colding. So this really says that the distance between any 2 points in R is actually realized as the infimum of curves, of lengths of curves that lie within R. And so this implies that the metric space X is actually isometric to the metric completion of this Riemannian manifold, this possibly incomplete Riemannian manifold. Okay. So let's say if for some reason you don't like metric spaces, then it's really enough just to look at this Riemannian manifold. This one contains all the necessary information. All right, so this is what we know about the regular set. And then the singular set is very small. Namely, it has Minkowski dimension. This is at most n-4, so codimension at least 4. And so the Minkowski, so that's stronger than the Hausdorff dimension. And then furthermore, we know something about tangent cones. So a tangent cone is a blow up at a fixed base point. It's just called a tangent cone. It doesn't need to be a cone. But we now know that in this case, tangent cones have to be metric cones. Okay? So this is a deep result by Chigger and Colding. And then we have some more structural results on the singular set. So we have some kind of stratification, which won't be that important for us, but I just wanted to write it down. Sorry, there has to be some complement here. I forgot that. All right, so this is the theory for Einstein metrics. And you may have noticed a similar theory for other geometric equations, such as minimal surfaces, harmonic maps, mean curvature flow, harmonic map, heat flow, and so on. Yeah. And so really, if I wanted to somehow write down the corresponding theories for these other geometric equations, I would have to go back to the previous slide and just change a few keywords and maybe adjust a few dimensions. But then the theory would be the same. Yeah. And the reason why this works for so many geometric equations is because this previous theory really only depends on a few very basic ingredients, like a monotonicity formula, an almost cone rigidity theorem, a cone splitting theorem, and so on. And once all these ingredients are established, then there's some kind of machinery that allows us to combine them and output this partial regularity theory. Okay. And it's somehow it's not hard to check all these properties, or it's possible to check all these ingredients for all these geometric equations. So that's why we have a theory for those. However, until recently, there was no such theory for Ricci flow. So Ricci flow was somehow maybe the outlier here. And in my opinion, this was because maybe some of these standard ingredients from these other settings were not available in the Ricci flow setting, at least a priori. So there was no almost cone rigidity theory, there was no cone splitting theorem, and so on. Okay? So this presented an obstacle. All right, let me see if there are any questions so far. All right, so this concludes the introduction. So let me now move on and state the main results concerning Ricci flows. Okay? And in a moment, I'm going to show you a pretty big theorem. And before doing this, let me just make a few key points to introduce us to this. So first of all, I want to demonstrate that there is a compactness and partial irregularity theory for Ricci flows. And we'll also have to, in order to state this theory, we'll also need somehow new parabolic notions for terminology such as metric space, Gromov-Hausdorff limit, and so on. Okay? Okay, so this was another obstacle why there has been no such theory for Ricci flows for a long time, because we just didn't have a good way of saying that Ricci flows converge in some kind of synthetic sense, or we didn't know what the limits were. And somehow, in order to somehow state this theory and also prove it, it became necessary to have some kind of new perspective on the space-time geometry of Ricci flows. And I'll present this towards the end of the talk in more detail. And we also, as I mentioned before, we need some kind of new approach towards showing partial regularity that bypasses the lack of some of these standard ingredients. So this is somehow not the standard way of showing partial regularity theory. So the proof of the following theorem had to somehow take a different route. All right, so let me now show you this compactness theory. And so you'll notice, so this is a long theory, but you'll probably notice two things. So first of all, the theorem that this theorem will be very similar to the case of Einstein metrics. So in fact, it will imply the Einstein case, up to some minimal work to translate maybe some terminology into the other. And then second, as I said, we'll use these some kind of new parabolic versions of notions from the Einstein case. And these are new notions, and I'm going to mark them in red just to show you that I'm aware that I haven't introduced them to you. Okay? So instead, I'm going to try to introduce them towards the end of the talk. But for now, I'm just going to give you some intuition. All right. So now let me start. So let me consider a sequence of n-dimensional pointed Ricci flows. Okay? So they're parameterized by these backwards time intervals. They stop at time 0. And the base points are going to be chosen out of the final time slice. So I claim that this makes the most sense. Then we can pass to a subsequence that F converges. So F convergence is now similar to Gromov-Hausdorff convergence. It's somehow the parabolic version of it, to a metric flow, which is the parabolic version of a metric space. I'm going to denote this metric flow by X, and there's going to be some other stuff there, which you'll see in a moment. Now, again, this could be possibly very irregular, but now we can impose a non-collapsing condition, which is now phrased in terms of the pointed Nash entropy at the base point. So the pointed Nash entropy is closely related to Perelman's W functional or mu functional. And in fact, a lower bound on the mu functional implies a lower bound on the pointed Nash entropy. But even the lower bound on the volume of a ball at the base point implies a lower bound on the pointed Nash entropy. So this is a very ubiquitous condition. So this certainly holds when we study singularity formation. Then it turns out we have a regular singular decomposition again of the limiting Ricci flow, such that the Ricci flow restricted to the regular set is given by a smooth Ricci flow spacetime structure. Right? So it's somehow smooth in the best possible sense. So Ricci, and this structure is the same thing that you may have encountered in my lecture series last week. So it's again like an n+1 dimensional spacetime manifold with some smooth structure on it, such that locally it looks like a Ricci flow. And again, X is again uniquely determined by this structure. So again, if you don't like metric flows, it's enough to look at this smooth structure. Then again, the singular set has codimension at least 4. And so here we have to assign 2 points to the time direction. So the entire flow has dimension n+2. And we're going to use what I call the Minkowski star dimension. And you'll see in a moment that this is somehow a reasonable parabolic version of the Minkowski dimension. Okay. So now, furthermore, instead of tangent cones, we now have tangent flows. They're just blow-ups again at a base point. And instead of cones, we have gradient shrinking solitons, because these are invariant under parabolic rescaling, such as cones, which are invariant under rescaling. And then we have a similar stratification result. Sorry, again, there's a complement missing, which is somehow the best, has some of the optimal dimensions. And again, I won't dwell on this one. All right, so this is this new compactness theory. So you'll see this is basically the same as for Einstein metrics, just that we have different words. Okay? And I'm going to give you more details on this theorem later. But let me first show you some consequences of this theorem. Okay? So first of all, regarding the folklore conjecture. Okay? And now I can really make this precise. So, or almost precise. I have to omit some details for the sake of brevity here. So essentially, the theorem now states that if we have a Ricci flow that develops a singularity at time t, then there's some way of taking a metric limit of these time slices. So we have some kind of metric space at time t, some kind of singular time slice at time t, such that if we take somehow the union of this space-time, m cross the half open interval, united with this, somehow singular time slice, then we can somehow view this as some kind of extension of the given Ricci flow, some kind of synthetic extension. And we will be able to take tangent flows based at points that are contained in this singular time slice. Okay? And when we do this, the tangent flows turn out to be singular gradient shrinking solitons with a codimension 4 singular set. Okay? So this is somehow the idea how we specify how we take blow-up models. So we don't say we take a sequence of points xi, ti running into a singularity. Instead of we say take some kind of the singular point and look at the tangent flows near these singular points. Okay? So these are going to be our gradient shrinking solitons. Okay? And so this approach is very similar to the mean curvature flow, for example. In the mean curvature flow, you can just take some point in the ambient space and say, I want to look at the tangent flow near this point. And then this gives you a blow-up limit. Then moreover, in dimension 4, we have some additional results. In dimension 4, all these tangent flows turn out to be given by gradient shrinking solitons on smooth orbifolds with conical singularities or isolated singularities. Right? So really, in this case, these tangent flows look like in Appleton's, what they look like in Appleton's result. And moreover, we either have positive scalar curvature or the singular gradient shrinking solitons are just quotients of isometric quotients of Euclidean space, so orbifolds. All right, so this is what we know about the Folkberg conjecture, regarding the singularity formation. Now, what do we know about regarding long-time asymptotics? Well, we can make a similar statement as what we've known in this three-dimensional case. Okay, so assume I take an immortal Ricci flow, so one that exists for all non-negative times. And then again, I'm going to omit some details. So for large y and t, we get that the manifold can be decomposed into a thick part and a thin part, such that on the thick part, essentially, if we take a sequence of points xi in the thick part, then somehow these blow down. So if we parabolically rescale by t to the -1, so make the time ti to be time 1, then we converge to a singular Einstein metric with negative Einstein constant. So we essentially, on the thick part, we're converging to an Einstein metric with negative Einstein constant. And again, in dimension 4, this flow is given by an Einstein orbifold with isolated singularities. And then the thin part is collapsed in the sense that some of the Nash entropy is very small. So this is similar to what we already knew in dimension 3. Okay, so these are somehow the two results governing short time finite time singularity formation and long time existence. But both of these results contain some kind of new terminology like F convergence or metric flows. Okay? So just to underline that this theory is useful for many other applications, let me just show you one result that doesn't use any new terminology that I can just write down. It's completely elementary. And this is called a backward pseudolocality theory. So it says the following. So let's assume that we have, in some Ricci flow, we have a lower volume bound at time t naught for a ball around some point x naught. And we also have an upper curvature bound on this ball at that time. Okay? Then we can extend this curvature bound backwards in time on some smaller parabolic neighborhood. Okay? Okay? So there's a theorem by Perelman called the pseudolocality theorem or forward pseudolocality theorem, where some of the only change is that this minus sign is a plus sign, okay? Where we can extend the bounds forward in time. Okay? Now we can show that we have the bounds backwards in time, and this was a result that hasn't been known before. Okay, so I think this has been attempted. At least I've attempted to prove this before several times, and it really needs this theory. All right, so maybe a few further remarks. So first of all, if we apply all this theory in dimension 3, then this essentially recovers all of Perelman's theory. So this is really a generalization of Perelman's theory in higher dimensions, or to higher dimensions. And also, maybe this is a weaker comment, we could, if we look at super Ricci flows, so where instead of equality, we have inequality, then there's a corresponding compactness theory, just as we have a compactness theory for spaces with lower Ricci curvature bounds. All right. Let me see. Are there any questions? Okay, so let me now move to part 3. So in part 3, I want to give you somehow a new kind of point of view on the geometry of Ricci flows. And this will help us understand some of the terminology that is the new terminology that's used in these theorems. And I'll provide some more details on the main results. And so in order to understand these new pieces of terminology, I'll need to review heat kernels on a Ricci flow backgrounds. Okay, so let me just put this relatively basic slide here. Okay, so I'm going to just be looking at a Ricci flow or defined over some time interval. And then let me look at two functions u and v defined on space-time. And there are now two equations that I can consider for these functions. Right? So these are defined on the Ricci flow. So first of all, I can look at the heat equation. So let's say u satisfies the heat equation, which is just the standard heat equation, but the Laplacian depends on the metric at time t. And this heat equation also has an L2 conjugate called the conjugate heat equation. Okay? And so we get some scalar curvature term here because we have some distortion of the volume form. Okay. So note this is some kind of backwards heat equation. We started some future time, and then this heat equation evolves backwards in time. And so the information of both of these heat equations is contained in the so-called heat kernel. Okay. So this heat kernel is defined for all xt and ys, so for 2 points x and y, where s is less than t, and it has the property that if we fix y and s, then for all later times, k satisfies the heat equation in the first two arguments, and it converges to a delta function at y as t approaches s. Okay? Then just by some kind of duality principle, this implies that if we fix the first two arguments, then this satisfies the conjugate heat equation, and it's actually a conjugate heat kernel placed at x. Okay. So K really contains the information of both of these equations, and in more particular via representation formulas. Right? So by this I mean that if we have two solutions to the heat equation or the conjugate heat equation, then we can write these solutions just by multiplying some given time slice of the solution against the corresponding heat kernel and integrating it against it. And then vice versa, we can do the same for v. Okay? So if you know u for some time s, then you can somehow compute u for any later time just by this formula, and vice versa for v. And we also have a reproduction formula for the heat kernel, which is some of the standard reproduction formula. Okay? All right. So what kind of properties do we have for these equations? Okay? So what is somehow, and I'm just trying to get some more geometric ideas out of these equations. First of all, if you just look at the heat equation, so the forward heat equation to the Ricci flow, well, we have a maximum principle. So upper and lower bounds on u are going to be preserved. Okay? And the same is true for the gradient of u. So if you compute the evolution equation for the gradient of u, then there's some kind of cancellation. So there's a Ricci term that pops up because of the Bochner formula, and also a Ricci curvature because the metric distorts by the Ricci curvature. And this will imply that the gradient satisfies a subheat equation, a subsolution to the heat equation. And so therefore this bound is preserved. But we can do a bit better. And this is somehow a new result now. Let me now state this result. I'll call this an improved gradient estimate. So in order to state the result, let me look at a very basic solution to the heat equation. So I'm going to look at a solution to the heat equation on just the real line R. I'll call it phi. And this solution should start with this step function because it's called the Heaviside function. Okay? So it's 0 for negative numbers and 1 for positive numbers. And then it's going to just evolve and smoothen out the step function. Okay? So this is just the antiderivative of the Gaussian. Okay? Now, this new result states that as long as we take a solution to the forward heat equation on a Ricci flow background that only takes values between 0 and 1, like phi does, then somehow the gradient of this function is always somehow smaller than phi in the following sense. So for any time t and for any point x, whenever I can do the following, I'll just locate an x prime on the real line such that phi is equal to u. And then once I've done this, then the gradient of u is bounded by the gradient of phi at that point. So phi somehow has the largest gradients given the value, its own value. And so this is even preserved for fixed t naught. So this gives me, and this is what I call an improved gradient estimate. So it gives me some better gradient control. So I'll get back to this result later. But let me just review what are the properties of solutions to the conjugate heat equation. Okay? So the L2 conjugate, the one that flows backwards. Well, first of all, non-negativity is preserved, but then any other bound is not preserved. Okay? We don't have a maximum principle anymore because of that scalar curvature term. But on the other hand, for a conjugate heat equation, we have this nice property that the integral of the solution over time slices is constant in S. Okay? And so this in particular implies that if we integrate the conjugate heat kernels over a time slice, then we always get 1, okay? The same constant as in the same integral as the delta function. Okay? And so this should somehow tell us that we should think of solutions to the conjugate heat equation more as densities of probability measures, okay? Things that integrate to 1. Okay? So I'm going to now, what I'm going to do now is I'm going to just change my point of view slightly. I'm going to view, instead of talking about solutions to the conjugate heat equations and viewing them as functions V, I'm going to view them as somehow probability measures, families of probability measures. And then for solutions to the heat equation, I'll just view them as scalar kind of Lipschitz functions. All right, so let me now, so with that being said.
Can I ask a question?
Yeah, sure. Yeah.
Go back to the previous slide, please.
Yeah.
Your improved gradient estimate, the assumptions on U is that it's a heat flow on a Ricci flow, right?
Yeah.
Okay, thank you.
Yeah, okay, thanks, yeah. All right, so, okay, so with that being said, let me just make one definition. It's a very basic definition. And instead of talking about a conjugate heat kernel, so this would be the conjugate heat kernel based at xt, let me just write down the corresponding probability measure. And I'll call this new xts, right? So essentially, I think of this as placing some heat here at x, and then flowing this backwards in time. And then at time s, we have some kind of probability distribution given by nu. In case just the density function. And then some of this has the advantage that, that if I evaluate this for s is equal to t, I can just write down what it is. It's just a delta function, okay? So that's just, I haven't done very much. I've just somehow put things in a nicer language, okay? All right, and then now this new language now allows us to write down these representation formulas and reproduction formulas in their own way. So for example, if something satisfies the heat equation, then we can write down solutions to the heat equation using this integral formula. And then similar properties hold for the conjugate heat flows. Again, I have to write them now down as families of probability measures. And we have a reproduction formula. Okay? So it's just the same equations that I showed on the previous slide, or 2 slides ago, I guess, but now expressed using these probability measures. So now the advantage of this perspective is that I can now tell you what a metric flow is. So recall a metric flow is a limit of a sequence of Ricci flows. Okay, so it's some kind of synthetic version of a Ricci flow. So what's a metric flow? So a metric flow is given by the following data, where x is a set consisting of points, t is a time function, okay, so that assigns to every point a time, and its level sets are just called time slices, okay? X, and I'll denote them by x lower t. Okay, so this may be reminiscent of what I've done in the Ricci flow space-time approach. And then dt is going to be a metric on xt. So as xt dt is just a complete and separable metric space for every t. Okay? So far, what we've basically done is we've constructed a family of, or maybe I should say a collection of metric spaces parameterized by a time parameter. Right? A priori, they have nothing to do with one another so far. Right? And so now I want to find a way of somehow relating them to one another, or relating points in these metric spaces to one another, to say what they have to do with one another. And this is now done using some kind of synthetic conjugate heat currents. Right? So what I'm going to do is for any point x and for any time s that's somewhat earlier, I'm going to choose fix some probability measure, nu xs. Okay? So I think of this as the conjugate heat kernel placed at x and then evaluated at time s. Okay? And I'm going to require, some of the properties that I wrote down before. So, if I validate at the same time, I should get the delta function at x, and I want the reproduction formula to be true. Right? So now this it gives me some kind of relation between points at different time slices, at least in some kind of probabilistic sense. And it also allows me to define heat flows and conjugate heat flows via these representation formulas. Right? So I can now say that what it means for a function on x to satisfy the heat equation just by saying it should satisfy these representation formulas. Right? And some of the last property that I now require is that the improved gradient estimate holds for these heat flows. Okay, there's a gradient contained in the statement of this improved gradient estimate, but I'm going to just phrase it in terms of Lipschitz functions. Okay? So this is the statement. Okay? So this object is now a metric flow. Okay? So this is the first red word that I can explain. Are there any questions? All right, so here's an exercise. So given a Ricci flow, how can I turn this to a metric flow? Well, x would just be the product of m cross the interval. T would be the projection onto the second factor. dt would just be the length metric for every time t. And then d nu xt, recall that somehow this pair is now a point in x, is just given by the conjugate heat kernel. Okay, so here are a few things to remark. So first of all, the distance between points in different time slices is not defined. And so I claim that this doesn't even make sense to talk about that. So, so I think that's good. And then the second remark is maybe a bit unintuitive. It's that some of this construction passing from a Ricci flow to a metric flow forgets world lines. So world line is just a curve of this form. So in other words, I won't be able to say, if I take 2 points in 2 different time slices, I won't be able to say whether they correspond to the same point on the manifold. Okay? So this information is just lost. Instead, the only information, somehow the information that's retained is some kind of probability distribution. So given some point x, I won't be able to say what is precisely the point at the earlier time, but I have some kind of probability distribution, what kind of the likely past of that point was. Okay? But that's all that I have. All right. Okay. So now I want to do some geometry with these metric flows. And so the first observation that I need to make is one that still uses Ricci flow, and it is a concentration property. That's essentially an additional property that I need to add. Okay. So let me state this concentration property. Let me first take just a probability measure, mu, on a metric space. Then I'm going to define its variance just by the double integral over the square of the distance function against that mu. Okay? So this is the variance. And I think some people might like to put a 1/2 here, but I like it this way. This just tells us how concentrated or non-concentrated mu is. And so here are some of the new theorem. It turns out that on a Ricci flow, if I take the variance of a conjugate heat flow, a heat kernel measure, then this variance is bounded by some constant times t minus s, where this constant is this weird form, which is weirdly optimal. Okay? So what does this tell us? And then, then we can use somehow this idea and say that a metric flow is H concentrated is if this bound holds for Hn is equal to H, and a little more, but that won't be important. Right? Okay? So in the following, we'll always assume that our flows are H concentrated, metric flows are H concentrated for some H. Okay? And essentially the purpose of this H is that it gives some kind of dimensional bound to the metric flow. So recall in the previous definition, we didn't have any mentioning of dimension. Okay, so metric flows could correspond to Ricci flows of arbitrarily high dimension. Okay? So assuming that they're H concentrated tells us somehow that they are, apart from them somehow having these nice concentration properties, gives us some kind of dimensional bound. And in addition to this, it somehow tells us that it gives us this nice property that the past of every point, which is somehow specified essentially by this conjugate heat kernel measure, is kind of determined up to an error of, the square root of this variance, so square root of t minus s. So we have some kind of way of saying, where somehow the past of a point was. Okay, so this is one notion. And then the other notion that I have to recall is the one Wasserstein distance. So let me just do this quickly. So if I take two probability measures on a complete and separable metric space, then I can compute a distance between these probability measures, either by taking this infimum over all couplings between the measures, or the supremum over all one Lipschitz functions. Okay? And it turns out that the W1 distance is actually monotone on a metric flow. Okay? By this, I mean the following. If I have a metric flow and I take 2 points x and y at time t, and I look at the corresponding conjugate heat kernel measures at an earlier time, then the one Wasserstein distance between those guys is bounded from above by the distance between x and y. And moreover, the left-hand side is non-increasing. And so this can be proven relatively easily. And essentially, philosophically, this means that on a metric flow, distances never shrink on a metric flow if we take diffusion into account. All right, so we have this monotonicity property. And now with these notions, I can define the notion of a parabolic ball. Okay? So what's a parabolic ball? So parabolic balls are used quite often when we study Ricci flows. And they're, what we would do early, in some of the classical setting would be to just say, if we want to have some kind of parabolic neighborhood of a point, then we would just take a ball of a point x naught at time t naught. Then we would just take a ball of radius r at that time t naught. I try to indicate this by this line here. And then take a product with an interval, going r squared in both directions, for example. Yeah. And so, these were very basic objects that we would work with, nothing spectacular. But somehow, the problem is that if we want to do this somehow same construction, that some of the same construction doesn't work on our metric flow, because the construction really uses the fact that we have world lines here. Okay, so that's the only reason we can take products. Okay? And so we can't do this anymore. Okay? And so now we have to come up with a different definition for parabolic balls in a metric flow. Okay? And so here is somehow essentially the only way this makes sense. Okay? If I take a point x naught located at some time t naught, then I'm now going to define the p star parabolic ball of radius r as follows. So I'm going to take all points x located in time slices between t naught minus r squared and t naught plus r squared, such that the following is true. If I look at the conjugate heat kernels at time t naught minus r squared, so at this initial time slice, so I look at the two conjugate heat kernel measures of x naught and x, then I require that the one Wasserstein distance between those two guys has to be bounded by r. Okay? So this gives me some kind of, the set of these points is some kind of neighborhood around x naught. And this is somehow a good definition of a ball in a metric flow. And it turns out that this is a very useful definition. So for example, standard containment properties still hold. So if I make the radius bigger, then the ball gets bigger and so on. And we have some relation between these two parabolic balls. So if we have curvature bounds, for example, these two notions are comparable to one another. And moreover, having these parabolic balls allows us to describe a natural topology on X, right? These essentially generate a natural topology. And we are also able to cover sets with these parabolic balls, and then this allows us to define the Hausdorff and Minkowski dimension, M star and H star. Again, we're counting the time direction twice. So now I've defined a metric flow, I've defined P star parabolic balls, I've defined these M star Hausdorff dimension. So maybe the next thing I should define or get closer towards is this F convergence, so the parabolic version of Gromov-Hausdorff convergence. So in order to explain this, I also need to review one additional concept, which I call the Gromov-W1 convergence. I know many people have a different name for it. Okay? So what's Gromov-W1 convergence? It's basically the same as Gromov-Hausdorff convergence, but where I replace Hausdorff by one Wasserstein distance. Right? Okay, so okay, so first of all, maybe I should say what is the distance, the Gromov-W1 distance. So if I have two metric measure spaces, okay, given by xi di and some probability measure mu I, then I define the Gromov-W1 distance between these two spaces just as the infimum of some of the push forward, the one Wasserstein distance of the push forwards, where I take the infimum over all isometric embeddings. Okay? So instead of a Hausdorff distance, I have a one Wasserstein distance here. With this distance, I can now define Gromov-W1 convergence, just like I would define Gromov-Hausdorff convergence. Okay? And so here's an important observation. If we compare this convergence to Gromov-Hausdorff convergence, we don't need to choose base points here. Right? For Gromov-Hausdorff convergence, if we choose non-compact spaces xi, we need to specify base points here to say that, you know, where somehow the center of our, you know, the approximate center of our spaces is. But now, since these probability measures have integral 1, you know, they have some kind of center. They specify where the center of this metric space is, and we don't need base points anymore. Okay, and so this is an important observation which we'll use in a moment. Okay. Now, with this definition, I can now loosely define what F convergence is. Okay. So consider now a sequence of metric flows xi over some time interval. And I'm now, instead of choosing base points on these metric flows, let me choose conjugate heat kernels.
Excuse me, Richard, there is a question.
I have a question from a previous slide.
Yeah. Mm-hmm.
When does the equality occurs in the Gromov-W1 distance?
Oh yeah, when the equality occurs, oh, then some of the supports of both measures are isometric. Okay, so I should maybe here talk about metric measure spaces of full support. Okay, so if we have equal, if the distance is equal to 0, then the two spaces, the isometric supports of both spaces are isometric. Does that answer your question?
Yes, it does. Thank you.
Oh, thanks. Yeah. So it turns out that somehow having full support is a very natural definition on this. Yeah. And as Christina mentioned, I think Sturm calls this convergence deconvergence. Or I think it's slightly different, but there's some kind of small detail that's different, but it's essentially the same. All right, so let me take a sequence of these metric flows, and I'm going to equip each metric flow with a conjugate heat kernel. Right? Okay, and so conjugate heat kernel now gives me a probability measure in every single time slice. Okay? Okay? And now I say that I have F convergence of pairs of metric flows equipped with conjugate heat flows to some other guy like this. If for almost all times, essentially, we have Gromov-W1 convergence. Okay? So again, this conjugate heat kernel takes the place of the base point here. Okay? It's some of the base conjugate heat kernel. Okay, maybe let me skip over these remarks. So this is how there's a theory for F convergence very similar to Gromov-Hausdorff convergence. There's a distance and so on, and we have a compactness theory, and we can really specify a set of these pairs that's somehow pre-compact and stuff like this. So it's very analogous to the standard Gromov-Hausdorff theory. Okay? And I should also say I'm omitting some details here. We need some extra properties how like conjugate heat kernels converge. But if you sit down, you'll see there's basically one way of doing this. Okay? All right. Let me now conclude with just one example. Sorry, what did I want to say? Okay, so this is F convergence. Let me just in the end show you one interesting example, and somehow put this all to work and show you why this was important that we somehow used exactly this approach and why we somehow forgot about world lines. And this example concerns the Bryan soliton. So the Bryan soliton is a rotationally symmetric solution to the Ricci flow. And so it is rotationally symmetric of this form where f somehow grows approximately like the square root of r. So I can write this down as some kind of raw product. And it's a steady gradient soliton. So all time slices are isometric to some of the same model. Now, let me call x pri to be the center of rotation here at time 0. This is, let's say this is time 0. Well, what I want to look at is now, I want to look at a sequence of blowdowns of the Bryan soliton. So I want to parabolically scale down the Bryan soliton. So that means I rescale all the time slices by a factor lambda I squared, which gets smaller and goes to 0. Okay? And then I have to rescale times accordingly. And I could ask, well, if I take a sequence of these blowdowns of the Bryan soliton based at this base point, what is the F limit? Okay? So I have to have, just by the compactness and partial regularity theory, I have to have some kind of F sublimit. And I could ask, well, what is this? Okay? Well, so let's approach this in a more naive way. Let's just pick some time slice, maybe time -1, and see what do these time slices converge to. Okay? Well, if I take a Gromov-Hausdorff limit based at this point, if I rescale this metric, all I get is a ray. Okay? So that doesn't seem right. That doesn't seem like it satisfies the partial regularity properties of the flows. Okay? But I want to note here that we've done something more or less illegal because I've said let's somehow take the Gromov-Hausdorff limit based at this point at time -1, which is just the same point x pri. So I've implicitly used world lines here, the concept of world lines, okay? And I'm not allowed to do this. So instead, when I take an F limit, I should look at the conjugate heat kernel based at this point, and then I should look where somehow this conjugate heat kernel is concentrated. Okay? And when I do this, if I look at the conjugate heat kernel, it turns out this conjugate heat kernel drifts away to the right at a linear rate approximately. Okay? So the center of the conjugate heat kernel is more or less here, where the flow is more or less cylindrical. And then it turns out that the F limit is actually here, the round shrinking cylinder, which might be a little unintuitive, but this is actually also, this has been looked at before by Perelman. This is called the asymptotic soliton in this case. Yeah, and so this is really a smooth flow. Okay, so I hope this underlines why this is important to look at these kind of these conjugate heat kernels and forget about our world lines. Okay, so I think I'm going to stop here. The last pages won't be that important. Thanks for your attention. And
thank you so much, Richard. So how many, are there questions?
I have a question. Can I ask?
Yeah, sure. Mm-hmm.
Yeah. If you have, say, in 3 dimensions, a neck pinch occur,
mm-hmm.
and then so you're going to continue beyond the neck pinch. So you're going to have slices that occur after the pinch, right?
Yeah. Mm-hmm.
What will be the distance between the 2 different sides?
The 2 distance, it would be infinite.
Okay. You said it to be infinite. Okay.
Okay. So I mean, that's a good point. You can, given some kind of, let's say, a singular Ricci flow, so one that somehow has a neck pinch, you could also construct a metric flow, but then you would have to allow infinite distances, or you have to somehow say which kind of branch of the flow you're going to follow. But
okay.
Either way, it makes sense. It makes sense also with this monotonicity property, telling you that distances only increase, then they become infinite. So maybe, another interesting case would be a case where we have an S2 cross S1 that has a single neck pinch and then becomes an S3. Okay? So if you take 2 points somehow very close to the neck pinch, they may have small distance from one another, but then suddenly after the neck pinch, they have large distance because you have to go the other way around. Okay? I mean, that would be be another example. So it's a kind of makes sense that the distances increase and that you somehow have no control over how much they increase.
Okay, so I have a second related question. Sturm had super Ricci flow, and in his super Ricci flows, which are not unique, and it's sort of only one-sided bound. It's like the Ricci non-negative goes to super Ricci flows. there was this splitting and possibility of putting distances between the 2 points that wouldn't be geodesic distances anymore. Is there any relationship between your flows and super Ricci flows? Or are they one of the super Ricci flows?
Not really. I mean, there might be some way of saying that you. So a metric flow should probably be more general. I don't know if you can turn every super Ricci flow into a metric flow, but yeah.
No, I wouldn't expect the super Ricci flows. I would expect them. Your flows have more conditions, so.
Oh no! So my flows should probably have fewer conditions. So I think you should be able to turn every super Ricci flow according to Sturm into a metric flow.
But you kind of have a two-sided Ricci bound, right?
I think it's just a one-sided Ricci bound. So the essentially I mean, somehow a metric flow, I would really view it like a metric space. It's just some object with very few conditions, just the bare minimum to allow a compactness theory. So we have the only times a Ricci condition enters is when we have this improved gradient estimate.
Yeah.
And that's essentially just a lower Ricci curvature bound. And then this concentration property. So as long as for these super Ricci flows, you can show that these two bounds hold, which I would seem is likely, then you could turn a super Ricci flow into a metric flow. But super Ricci flows are a bit more restrictive in the sense that you know what a world line is, and all time slices I think have to consist of the same points. So they have all time slices somehow have to be homeomorphic to one another. And super Ricci
No, I don't believe so, but okay, yeah.
Oh, maybe that's wrong. That's wrong.
They had super Ricci flows that broke apart, but
okay. Sorry, I'll take that back. Yeah.
But they gave up on the geodesicness. Are your slices of geodesic metric spaces? Or they may or may not.
Yeah, almost every time slice is geodesic. Wait, sorry. You can make them in such a way that essentially the super Ricci flows is only interesting up to a zero set of times, and then you can on that zero set you can choose them however you want. So you can make them geodesic in every time slice, or you can make or they're just geodesic for almost every time slice.
Okay.
But they don't satisfy a doubling property, for example. So I don't think a doubling property makes sense in the context of Ricci.
Very interesting.
Some of the restriction of the Sturm construction was that in the Sturm construction you could only take limits if you had a uniform lower Ricci bound. It could be a very negative lower Ricci bound, but you needed some lower Ricci bound, and that's very restrictive. For example, if you take a neck pinch, just a simple neck pinch, you don't have a uniform lower Ricci bound. So this theory does not require any uniform lower Ricci bound. I mean, it requires the Ricci flow equation, but yeah, nothing more. So even though the time slices really converge without having that much more control over the geometry. Yeah.
Interesting. Thank you.
Does this answer your questions?
Yeah, that's good.
Yeah, thanks for the questions.
Thank you.
Okay. Are there more questions? So there is a question in the chat.
Oh, okay. Okay, but maybe let me answer the question in the chat first. Can we expect finite time singularity models on R4 modulo ZK with k bigger than 2 in general, or in Appleton's example? I think that's a hard question. Appleton's construction was quite technical and was about 120 pages. Then if you look at the corresponding models for R4 modulo Z2, I think you don't have U2 symmetry anymore. So the best you can hope for is somehow some kind of T2 symmetry. Yeah, I wouldn't know how to show it. I would expect, well, in Appleton's example, it's not quite clear whether they actually, in what sense these singularities show up. But I think that somehow whatever occurs in Appleton's example should probably also true if you look for R4 modulo ZK. But yeah, I don't know. The theory more or less tells you that if this happens, it's not such a big deal, but it doesn't really help you construct these examples. yeah, I hope that this answers your question. Yeah.
May I ask a question, Richard?
Sure. Mm-hmm.
So yeah, thank you very much for your talk. So what I would like to ask is, if you so is the theory it is to control the first singularity, or do you want to pass it like what you did in 3 dimensions?
Or do you want
to go past the singularity?
Oh, to pass it. Oh, yeah. I mean,
or
okay,
is it absolutely out of reach?
I don't think it's out of reach. So no, I mean, that's a good point. I mean, somehow for now, the task is just to understand the first singularity. But of course, the hope is that the theory is flexible enough to allow you to flow through the singularity. So that if, let's say like this, if you can flow through singularities, then this compactness and partial regularity theory still makes sense. So it basically transfers in the same way. So if somebody gave you an already kind of, solve your problem for you, you would have compactness and partial regularity properties.
Mm-hmm.
And you would be able to say what these flows look in their singular set. And you would be able to say that these flows more or less look like neck pinches or some conical singularities and so on. The problem is, how do you construct this flow? Like, so you would probably, if you go to the first singular time, we know that somehow the singularities look very close to neck pinches. So I'm still working on this, but I think I could basically write down a way of cutting out all the singularities so that we have some time slice where we can restart the flow. Yeah. But turning this into some kind of, continuing this several times will take some work, and coming up with some kind of Ricci flow with surgery. But I think most of the ingredients should be there. Yeah. And then what you should get in the end is, again, a metric flow with exactly the same regularity properties. And maybe I should say, in dimension 3, these regularity properties are already true. So in dimension 3, we have a singular flow, and the set of singular time has Hausdorff dimension bigger or equal to, at most 1/2, and that's exactly the same dimensional bound that somehow that was predicted by this partial regularity theory. So, yeah, but yeah, that's the ultimate goal, to flow through singularities at least in dimension 4, let's say.
Many thanks.
Thanks. Yeah, thanks for the question.
Some other question? Okay, so if this is not the case, we thank Richard again for this beautiful new notion, and we'll see. Maybe we'll see each other tomorrow.
Yeah. Mm-hmm.
Have a nice day, Richard.
Yeah. Have a nice evening. Bye. Thanks again.